welcome again. So today's lesson will be on the chemical earth module in Year 11 chemistry. And in the previous lesson we looked at elements and compounds and mixtures. And in today's lesson we're going to look at the first type of bonding, and then we're going to cover 4 types of bonding, but the first one will be metals and metallic bonding. Okay? We're going to see how metals get their properties from this particular bonding structure. And here we have a variety of metals. Hopefully you can recognize some of them. And you can see that some of them are different, but these properties that we're going to talk about will all be the same among most of these metals. Okay? So metals. Pure alloyed metals have special properties that are often exploited in industry. That's pretty obvious. We see metals used all the time. Cars, building structures, you name it, it's probably made out of metal. Okay? And the reason is they have special properties that allow us to do things. Electrical conductivity is one of them, a major one. Strength, malleability, ductility are all really valuable properties that industry likes. So electrical conductivity is great for us as humans because we really like using electricity for things. Strength is good because we like building buildings bigger. We like planes moving really fast. Malleability, we like to make these things easily. And ductility is drawing out wires to use in our electrical systems. So all of these are quite useful properties, and that's the properties that most metals possess. And these properties can give us insight into the structure of metals. Okay, so the properties kind of infer certain details about the metals, but there's more to it than that. Okay. So the metal structure, what is the metal actually? Well, the metal consists of a 3-dimensional lattice of positive ions, and these are the nuclei of the atoms, surrounded by a sea of delocalized electrons. Okay, so there's a lot of words there, but the key thing is that you've got a lattice, essentially, of these positive ions. Okay, so if you imagine it going into the board as well, you'd have like circles going into the board as well, and that's what we call a 3-dimensional lattice because it makes like a 3D shape. And the nuclei of the atoms are all positively charged because they have protons inside them. Okay, so we remember that from probably Year 10. Now the key thing is that the electrons in the outermost shell, the valence electrons, so to speak, they're not bound to any particular atom. Okay, so this electron doesn't belong to this atom. Okay, and that's what we mean by delocalized. They don't have a set location, so they're free to move in whatever direction they want. Okay. And that has particular implications for its properties. So you can see that each of these electrons is moving in different directions, random directions, and they're not bound to any any atom. So that gives it unique properties, and we'll talk about that in a sec. Now it's the attraction between the positive nuclei and the negative electrons that keeps the crystal together. So the fact that this electron may be attracted to this atom sort of keeps the lattice from repelling itself apart. Okay, so that helps to keep it together. Now the delocalized electrons, let's look deeper into what that actually means. So instead of having the circles, we're just going to have the minus signs because it's a little bit easier. Okay, so delocalized electrons are the valence electrons of the atom, like I mentioned before. Now since metals only hold their valence electrons weakly, so you should know that, like sodium wants to always get rid of its electron, its valence electron. So most metals will only hold their valence electrons very weakly. These outer electrons are then free to move through the lattice of the material. So they're happy to move between the ions however they please. Okay? Now that's why metals are excellent conductors. Okay? So just think about that for a second. If these electrons are free to move wherever they want, if we apply a voltage across them, then the electrons will all be attracted to the positive end of that voltage. Okay? And then they're free to move to that voltage if they want. Okay? So that means that there's this big movement of electrons, which means there's a big movement of charge, which is essentially what electricity is, just the movement of charge. So if you see that all these free charges are allowed to move to the positive end, means that metals must be excellent conductors because those electrons are all free to move. And if you look at it, metals are all good conductors, or most of them are very good conductors of electricity. So that this model really helps us to explain the properties that we see in metals. Okay. Now, the electrical conductivity we've just explained, but what about ductility, malleability? Okay, how come they exist? Why doesn't the lattice just explode into a million pieces when we hit it, like a diamond does? Why does it just bend and warp? Okay, so that's our next question. So, because each of the ions is really closely packed, because it's a highly dense material, the nuclei are very close together. Okay, so the nuclei, so these guys are quite close together. Now, since the electrons aren't bound to any particular atom, layers of atoms can actually slide past one another while still being bound to the structure. Okay, so here we got the normal lattice. This is just a plain metal. Then we've applied some kind of force to the top half. Okay, we've hit it with something. And you can see that the top half can actually slide across, but it still remains attracted because there's electrons in between. Okay, so the electrons in between are actually holding the lattice from falling apart, but it's allowed these top ions to actually move across and slide. And that's why metals are ductile, because if we can slide and rearrange the atoms accordingly, we can actually form new shapes. And so that's why they're malleable. Or in the ductility case, we can draw it out, sort of stretch these layers and hopefully get them to collapse in on each other, and then you get a wire. Okay, so these delocalized electrons actually help to keep the structure while it deforms. Okay, so the electrostatic attraction between metal ions and electrons is still held, even though the atoms are actually moving past one another. And this obviously gives the metals good malleability and ductility. Okay, so that concludes today's lesson on the metallic bonding and metals. We looked at the metal structure, what delocalized electrons are, and why that has implications for the metal properties. Okay, so we'll move on to the question segment. Hopefully you can develop your knowledge, or at least expand it with these questions. So metal nuclei are positively charged, however they are found to be closely packed in metal substances. What stops the ions from repelling each other? So like I said, each of the ions is really closely packed together, but how come they don't just repel each other and destroy the crystal? Well, the delocalized electrons move through the lattice and attract adjacent metal ions. So if there's an ion here and an ion here, if an electron goes past, right, the electron goes whizzing through, it will actually attract both of these together, obviously, because if a negative charge is in the middle, obviously they'll attract to one another. Okay, so that's what the first statement is saying. Now this stops the structure from breaking apart because the repulsion of the nuclei is now sort of counteracted by the attraction to these electrons. So the repulsion, because of the positive charge, is actually counteracted by the fact that you've got all these electrons randomly distributed throughout the material, which helps to hold the lattice together. So it's sort of a very fine game that we're playing with metals, that each thing is sort of nicely balanced with the next. So explain why delocalized electrons lead to excellent electrical conductivity. So electrical current is the movement of charge through a substance. Okay, that's what electric current is. Since there are many free charges in metals due to the delocalized electrons, because there's lots of them, large electrical current can be generated because all of them are free to move, and so that's why delocalized electrons give metals excellent electrically conductive properties. Okay. Now, that was electricity, but what about heat? Metals are really good at conducting heat. If you, for instance, put a metal spoon in boiling water, you don't want to touch that spoon about a minute later because you'll burn yourself. So that obviously shows us that metals are good at conducting heat, but why? Okay. So heat is transferred through a metal by vibrations. Okay, so if you've got one ion being heated up, it will shake like this. Now, if there's another one sitting here, it will continually bump into this other ion, like a really annoying, bus passenger or something. and then this one will start vibrating, and that will keep going sort of like a chain effect down to the so that all of the ions are actually vibrating. Now, since the metal atoms are close together, vibrations can be passed very easily to one another. So imagine if I was standing here with someone standing here. If I was to start shaking, they would just be fine. But if we were right up next to each other, then if I started shaking, they would start shaking as well, because just to get out of the way. So the fact that they're so close together means that vibrations can be easily passed along from one atom to another. Now, another reason why they're good at conducting heat is that the fact that the delocalized electrons also help to transfer heat as their motion is increased due to the fact that there's heat energy around. So an electron moving around might bump into an ion and make that start vibrating. So you can see that if you've got a lot of electrons around, there'd be lots of collisions and lots of shaking, and the heat will get transferred very rapidly, in addition to all these other vibrations happening through the lattice. Okay, so that helps. This means they are likely to collide with metal ions, creating more vibrations, as I mentioned. Okay. Question 9, why are metals malleable? Answer with regard to metallic bonding. Well, due to the close packing of atoms, layers of metal nuclei can actually pass over one another. And the strong attraction between the metal ions and the delocalized electrons stops these layers of metal nuclei from completely detaching, and thus allow the metal to retain its shape. So as they slide along, they still are held to the other atoms. It's just that they've been moved along by a force, and so the actual metallic bond helps to hold the metal in shape as we change its new shape. So question 10, metals are considered to have a high boiling and melting point. Explain why this is so. Okay, so why would metals have a high boiling or melting point? Well, the attraction between metal nuclei and electrons form a very strong electrostatic attraction. So when you have the nuclei of the metal, you've got these very big positive charges, and you've got all these negative charges swirling around them. So the attraction between those two is very, very strong. And that ensures that the metal nuclei are kept in the same place rigidly. So the metal nuclei are always held in place by these electrons and protons. Therefore, in order to melt the liquid, in order to melt the metal, high temperatures are required to overcome the strong force of attraction between the metal ions and the electrons. So that concludes today's lesson on metallic bonding and metals. We looked at what metallic bonding is, and we explained the properties of metals through the metallic bonding model. Okay? So hopefully you've learned something about how metals operate, and I look forward to seeing you at our next lesson.